Hello everyone, my name is Sikai Wang. I am honored to be here to participate in the CGI conference and share our work, LiteCortexNet, towards efficient object detection at night. We work with the intention of solving practical railroad maintenance problems. Well, railroad workers often maintain the railroad at night and often have to use various railroad work tools such as spike hammers, road picks, forks, and wrenches. During the handover count, it is often found that various tools are missing. The inventory was manually checked in the past, which was time-consuming and easy to misjudge. We try to automatically inventory specific railroad tools in night field scenes by a deep learning object detection algorithm to reduce property loss. Deep learning-based object detection models work better in well-imaged, well-lit scenes. However, object detection in low-light conditions at night is still a challenging task. Many recent works have tried to solve this problem by incorporating night vision devices such as LiDAR and infrared cameras. This approach can achieve high detection accuracy, but the requirement of expensive equipment limits its application. To improve the accuracy of nighttime object detection, the most intuitive idea is to compensate for the image's illumination component to enhance the object's visual features. One commonly used illuminance estimation theory is Retinex, a theoretical model for human visual perception of luminance and color. Its theoretical basis is that the color of an object is determined by the object's ability to reflect light, not by the intensity of the reflected light. The color of an object is not affected by the non-homogeneity of illumination and is consistent. In recent years, the combination of physical and data-driven methods for image illumination estimation has become mainstream. For example, Retinex method is used to manually enhance nighttime images to train a pedestrian model, which obtained higher accuracy than the model without training enhanced images. However, much of the existing related work is still based on offline data augmentation, and an end-to-end deep learning-based nighttime object detection pipeline has not been established. We built a night railway object detection dataset. We went to the railway lines in some areas of China and took 8,318 photos of railroad workers taking inventory of working machines with cell phones and digital cameras. After that, we used rectangular boxes to precisely mark the various types of tools in the photos. There are three main challenges in our project. Firstly, images taken at night under artificial light may suffer from low illumination and uneven brightness, which makes them significantly different from pictures taken during the day in terms of image characteristics. Secondly, there are many small observation objects in our dataset. Thirdly, to control costs, our project required using only RGB cameras and not introducing other sensors, which limits our use of professional equipment such as night vision. We proposed LiteCortexNet, a novel deep learning object detection model, to tackle the challenges. It uses a data-driven approach to convert obscure features in the RGB domain to the reflection domain for analysis. It detects objects in nighttime images by fusing RGB and reflection domain features. A depth-separable convolution-based neural network is used to extract the RGB features of the object. Compared with conventional convolutional layers, depth-separable convolution has fewer parameters and higher computational efficiency. The feature pyramid and efficient channel attention module based on equivalent convolutional stacking operations are introduced into the detector to solve the detection problems of small objects and obscure objects, respectively. We proposed RCG to solve the image domain transformation problem. Well, an image can be decomposed into a light component and a reflection component. The reflection component is a constant determined by the nature of the object itself. In the training phase, the RCG is expanded into a two-branch parallel network with shared weights and is trained with dark light image pairs. The output feature mapping is compressed into feature vectors, and the cosine distance between the two vectors is to represent the similarity of the reflection components predicted by the two branches. According to Retinex's theory, the reflection component is independent of the illumination. Therefore, the output of the RCG dark branch feature map should be as similar as possible to the output of the bright branch feature map. Finally, in the test phase, either branch is taken out individually. The reflection properties of the object are essential, but its basic RGB properties cannot be neglected in object detection. Well, in this paper, a fully depth-separated convolutional neural network is used to extract the RGB features of the object. The depth-separable convolution has fewer parameters than conventional convolutional layers, thus improving computation efficiency. There are two common complex problems in the field of object detection: small and obscured objects. As for the first problem, classification tasks require feature mappings with higher-level semantic information. These feature maps are usually located deeper in classical CNN structures. However, due to translation invariance and downsampling operations, deep feature maps lose a large amount of object location information, which is not conducive to coordinate regression. The bounding box regression task requires feature maps with more detailed spatial information. These feature maps are usually located in shallower layers but do not have complete semantic information, which is not conducive to object classification. As shown in the figure, we use a bottom-up path for the forward propagation of the neural network. After convolution, the feature maps typically become smaller, and we use the top-down path to upsample the more abstract and semantically advanced feature maps, and then merge the upsampling results with feature maps of the same size generated from bottom to top using the lateral. Each layer of prediction uses a feature map that incorporates features of different resolutions and semantic strengths, allowing the detection of objects with widely varying scales. As for the second problem, we introduced an attention mechanism to increase the weight of valid objects in the feature map. The ECA module can adaptively extract useful information around salient objects using one-dimensional convolutions, thereby efficiently highlighting object features and suppressing background features. Therefore, our detector can pay more attention to the object's location and ignore the background. We designed a comparative experiment to verify the effectiveness of our method. Overall, our model is a lighter weight and higher performance model compared to the results of the baseline approaches. On average, all models achieve the highest detection accuracy on oxygen and gas tanks, mainly because these two objects usually have a large scale in images. In contrast, accuracy for small-scale objects such as wrenches and hammers is relatively low. Our model achieves higher accuracy for such small objects than various baseline methods. In addition, objects with poor surface reflectivity, such as wires, are not distinctive at night. Our model benefits from the reflective properties of the object calculated by the RCG, and the recognition accuracy of such objects is much higher than other methods. As can be seen from the rightmost figure, our method can more accurately detect objects with uneven illumination, large-scale variations, and partial occlusions. However, other baseline methods cannot handle the above cases well. For example, in the fifth column of the figure, CenterNet incorrectly identifies a wrench as a hammer, and SSD does not detect the toolbox behind the error frame. Besides, in the first column of the figure, YOLO V3 and YOLO V4 have poor performance in identifying and locating wires in dim light. These results demonstrate the feasibility and effectiveness of the model proposed in our paper. We also designed generalization experiments to demonstrate the performance of our method on different domains. While XDark is one of the recognized low-light object detection datasets, we choose this dataset to test the generalization performance of LiteCortexNet in different nighttime scenes. After 500 rounds of training, our method achieves an MAP of 94.4%. Figure A on the right is the original image input into our model for prediction. Figure B is the reflection feature map calculated by the RCG, and C is the visualization of our model's outputs. Our method shows high detection accuracy on the XDark dataset, and RCG still properly performs the reflection component decomposition of the images, indicating that our method can generalize with a high degree of interpretability. Some of the references cited in this slide are shown above. Well, here concludes the presentation. I appreciate your interest in our work. Thank you very much.